Okay, so for Monday, these are the problems. We probably won't work these in class. We'll just turn them into me on Monday, and then I'm going to work on grading these. But the problems for the chapter are 2.1, 2.1 A and B, 2.2, 2.4 A, B, D, and F, and 2.5 A and C. Okay. The reason why I'm kind of cherry picking these is because I took the ones out that deal really with the anions and the cations. We're not gonna delve into that area. It's just not. It's more theoretical than it is practical, and so I'm just not going to take us down that road. It's not real super helpful. So anyway, these are the ones that will turn into me on Monday. Okay. So let's go back and let's look at where we've been, where we're headed. We know our Woodward-Hoffman rules. We start with 4N thermal con. Okay, so 4N thermal con-rotatory. All right, again, that's where it all starts. So we're gonna jump in, and I'm gonna go back over this because I want us to see really what's going on with these reactions. So if I have some form of a reaction that looks like this, I know that I can go back and forth to this thing opening up. Okay. So if I am 4N, typically 4N prefer to open up. Okay. 4N plus 2 prefers to cyclize. And that should make sense somewhat from, again, the alkene ring strain in a 4-membered ring is a really strained system. So it's going to prefer to open up. So with this, then what we want to really focus on, and I kind of think of it more like this. I like these things more in kind of more of a three-dimensional realm, coming out at us like this. Okay, and so that helps us with really where our lobes are. Our lobes are here, our lobes are there, and then our lobes are here. Okay. So that's really what we're talking about. So with this system, then we're going to derive our orbital set. So our orbital set is going to look like this. All right. This is going to be psi, or excuse me, sigma. This is going to be psi 1, psi 2, and sigma star. Okay. Energy, of course, is increasing. With that, then, I get really nice overlap here. My lowest overlap here, my first node here, and my first node here. Okay. So we really left off looking at this in a context of symmetry elements. So I'm going to draw the symmetry element. I'm going to draw the other set here for the reaction. Let's go ahead and use black. So if we did that, we're going to, again, draw our 4 sides. Okay. So as I draw my symmetry, or my orbital nodes, 0 nodes, so low energy, 1 node, a little higher in energy, 2 nodes, and finally 3 nodes. Okay, this is really where we left off, talking about the 4N and its symmetry elements. So with this then, what became really important was what symmetry element am I talking about? If I'm talking about a plane, on a plane, or a rotation, or a rotation. Okay, so depending on how I think of this, I have a plane of symmetry, again, that becomes symmetrical, symmetrical, asymmetrical, asymmetrical. With rotation, this remains symmetrical, this is asymmetrical, this is now symmetrical, and this is asymmetrical. Okay? So really what happens is our sigma doesn't change. Our sigma bonds stay the same symmetry element, no matter if it's a plane or if it's a rotation. Okay? What flips is the symmetry of the pi bond. Okay? That's really what's taking place here. So when I look at the symmetry elements of my product with a plane, I'm symmetrical, asymmetrical, okay, plane, symmetrical, and asymmetrical. When I look at rotation, I'm asymmetrical, so asymmetrical, and then rotation is going to be symmetrical, asymmetrical, and symmetrical. So for the most part, when I'm looking at my pi bonds on the product, these all invert, okay? Whereas my sigma stay the same. So that's why if I'm looking at my symmetry elements, again, a plane of symmetry, okay? A plane of symmetry, if you think about that, a plane of symmetry is our disrotatory. So a plane is dis, and a rotation is con. Okay, so that's really the breakdown of what we see going on here. All right. So with that, let's see how we're doing here. I think we can see all that good. Okay. So that's why when I have 4n thermal con rotational plane, or going from symmetric to symmetric, asymmetric, asymmetric, I see that this crossing is allowed. Does that make sense? Whereas I have to jump in, if I'm the blue, I have to go up. This one stays again. Let's see. Yeah, this one stays the same. Okay? So that's why the disrotatory in a 4n system is what we call forbidden. Okay? So we start with 4n thermal con. All right? Does that make sense? Any questions on that before we complicate it?
But this part.
This part?
Like the rotational and plane are the same. Like
here and here?
Like for the
here?
So there's the diene, right?
Yes.
And there's this part.
The cyclobutene?
Their rotation and plane symmetry are the same. Like
for sigma.
For like everything. Like ASAS and then ASAS. For rotational and plane.
For rotational. Yes, they're the same. Yeah. So, symmetric, asymmetric. Again, lower energy. I'm feeling the 2 electrons. Because remember, out here where my electrons are, I only have these electrons. Okay? So with I don't want to have to go up to the LUMO if I don't have to. I don't think I'm following your question, John.
Is it possible to connect the phase of a rotational to a plane?
Rotation to a plane, no. Rotation is a different symmetry element than a plane, right? Rotation is when this flips over. So there's a point right here where this is going that way. And relative to that point, it's asymmetrical. There's a point here, and when I rotate that over, it's symmetrical because it's the same thing.
Cause I just see a pattern like this one's the same, like this is the same, it's the same, like for rotational plane.
Oh, you mean like green going to blue? Green going to blue? Yeah, you can't. It doesn't. They're different. They're different symmetry elements. Okay, and it deals with the fact that one is dis. That's symmetrical to a plane. Con is symmetrical to 2 points of rotation. So you can't cross those symmetry elements. No, okay, that's a good question. I hadn't thought about that. You're seeing A to A, S to S. Yeah, it doesn't work that way. You have to stay with the same symmetry element. So blue has to go to blue, so it has to jump up. Okay? All right, so that said, and I won't drive, I do the 4 because it's a little bit easier to do than the 4n plus 2, but you know the rules are there, and it's going to be the same reason for. I'm going to move this a little bit here just so I can put the electrons in. Okay, so how did I do that? I'm going to put the electrons here. So my electrons are here and here. So this is sigma. This is psi 1, psi 2, and sigma star. Okay. So those are really my, and if I want to keep this completely consistent, I'll draw these in over here. So that's there, that's there. This is psi 1, psi 2, psi 3, and psi 4. Okay. Now, we start with 4n thermal con. And from 4n thermal con, we get 4n thermal con, and we get 4n plus 2 thermal dis. Okay, so that's what we left off talking about. This is the rationale. Now, we're going to move on into photochemistry. What is photochemistry? Photochemistry, of course, is the excitation of pi bonds. Make sure it's still recording. Good. Okay, so photochemistry, which we're going to have a chapter at the end of the semester on photochemistry itself. We're going to talk about T1 and T3 transition states, but right now we're just talking about photons. If I'm in the UV region at about 273 nanometers, that translates to about 105 kilocalories per mole. That's a lot of energy. Okay, that's a lot of energy. So what happens with these systems? Is we can then take a lot of energy and pack it into a molecule by exciting the pi bonds. So for example, if I take this 1,3-butadiene under UV around between 250 to 300, I do get out some of this, okay? And you can see how we get that. If we draw this like this, what you can see happening with this is we get an electron here, an electron here, electron here, electron here, okay? So we get this excited state, if you will, and you can kind of see how that goes to this molecule. I also can take this and get a bicyclo out of this thing. Okay? Again, very high strain energy. We're talking 105 kilocalories per mole is quite a bit of energy. And this you can see coming literally from this crossing over. Okay? So an electron comes out here, an electron comes out here. What you actually end up with is, if you draw it, this here, boom, and boom underneath, and which is exactly what that is, okay? So you get, with photochemistry, some really unique, kind of weird structures. the question that we want to ask is what's going on and how are we exciting this and how do we see this playing out with our rules? Well, if you actually excite benzene the same way, this happens to be the one we've been talking about here with our cyclobutene, which is why I want to be consistent with that. And you excite benzene itself with photochemistry. Okay, so if we excite benzene, we irradiate benzene with photochem, you get a couple very weird compounds out. One of them we call duorbenzene, which looks like this. Okay, that's duorbenzene. We get out prismane, which is a bizarre compound. And we get out another bicyclo, very similar to our 3, but in this case, it's a weird, I'm gonna run it differently. Okay. So you see, and you could move electrons around on those and figure out where they're coming from, how you're getting that, because you can see that this is going to be just literally moving to the middle, that and that to form that. You could also do it across here, okay, and then you can cross over again to form this one, and you can see that these weird electron movements. Why? Again, because of photochemistry, it's a high energy yield. You can get really weird, interesting things. Now, granted, these things don't last very long, okay? You can photoirradiate them, they form, but then they go right back to benzene under thermal conditions. Okay, so it's not like, duorbenzene you can actually isolate, but it's still not very stable. These other ones aren't stable, they just decompose. Okay, so photochemistry then adds an incredible amount of energy to the system. But what's going on with the photochemistry process? Well, it's kind of an interesting thing. And I'm gonna let's see, I'm gonna leave that up because I want to come back to it. So I'm gonna erase. You guys have that written down? Those things written down? Yeah. I'm gonna erase this. I'm gonna stay here on this chalk or this whiteboard. Yeah, because I want to keep that one up over there. And I'll have to redraw that. Okay. So here's what's happening with photochemistry. Actually, it's kind of an interesting thing. If you actually follow in our textbook and go back to the back of the chapter 2, and look at reference 29. This is my professor at Berkeley, Professor Dalvin, Bill Dalvin, who did this work.
That's cool.
Yeah, it's actually pretty cool to have your own postdoc grandfather listed in some of this groundbreaking photochemistry work. So when he irradiated this, and his postdocs irradiated this, they got out something very specific. And what they got out was this. Okay. So under irradiation, they were able to force the diene to form the ring. Okay? So the question is, why was this the only one? Why this and not this? Okay, and you can be thinking this through. This comes back down to doing our pinky thumb chemistry, this time our thumbs being the methyl groups. Why is it going in a disrotatory fashion? Because that's exactly what's happening here. If my pinkies are the alkenes, okay, and as they come together, they're going up. So they're only going in a disrotatory fashion. So what's going on? Why is it that when I irradiate a 4N system, it goes dis? Well, if you go back and remember, when we have 4N thermal con, what we're seeing is 4N photo dis. Okay? So it flips. Why? What's going on? Well, what's believed to take place is when you photoirradiate a system. Let's say we photoirradiate this system. We're adding photons to this. We're actually exciting one of the alkenes, especially if we do it around 270 nanometers. If we go below 200, by the way, you blast the molecule apart, way too much energy, and you get lots of bizarre stuff that's not predictable. But if we're in that sweet spot of about 270, what happens is in the diene itself, we excite an electron. Okay, so watch what happens. If I take this electron and I excite it, okay, something changes with my symmetry function. And now all of a sudden, what made sense before in my plane of symmetry or my disk rotatory or con rotatory, depending on which one we're looking at, foreign thermal con, notice what happens to my symmetry elements. Okay? So now when I put an electron here, what happens to my symmetry elements? Well, what you see happening is now all of a sudden you have ASA and you have SAS, or you have SAS and SAS. So now with the photochemical reaction, so the thermal, I'm going to put this back here, so the thermal, whoops, not there. Thermal prefers to go that way, photochemical prefers to go that way. You've excited the alkene. Now watch what happens to my symmetry. So blue, 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 right? You're in an excited state, but my symmetry lines up in order for my orbitals to form over here. Whereas when you're in an excited state, notice what happens with your rotational, okay, or your con symmetry. A goes to A, S goes to S, but now look what happens. A has to go up to A, to a higher energy orbital.
Gotcha.
And that's forbidden. Okay? So again, since we have side 3, side 2, side 1, we've added energy to the system. So now I've got 3 orbitals that have to have symmetry aligned. So again, my lowest crosses over, my asymmetrical crosses, my symmetrical crosses, and I'm allowed. If I had to do like we saw the con with, then A goes to A is fine, S goes to S is fine, but it's this one here is forbidden. Okay? That's the one that's forbidden. So that's why with these systems, we end up with 4N thermal con, where we start the entire process. We end up with 4N plus 2 thermal dis. Now we see 4N photochemistry dis, right? And we're going to see 4N plus 2 photochemical con. So there are your 4 rules. And that's what I like to think of this all starting 4N thermal con, 4N thermal con, 4N thermal con, all starts there. Everything else makes sense because it's backwards, right? It's just flipped. If it's 4N, then 4N plus 2 is going to be the opposite. If it's 4N photo, if it's thermal and photo, it's going to be opposite. If it's 4N photo dis, it's going to be 4N plus 2 photo opposite con. Okay? Again, all starts there. Yes?
Question. For the rotational of the A where it's forbidden,
I forgot to bring Zach with us. Hang on. Go ahead.
for the rotational of the A where it's forbidden,
Yes.
where does the A should be connected?
Where does the what?
The A should be connected.
This A?
Yes.
It should be there. Green has to go to green. Green can't go to blue.
But if it's forbidden, like,
Yeah.
where should that A be?
What?
If that is forbidden, right?
Yeah.
Where that A should be?
John, I don't know what you're asking. Where does this A? This electron, because of symmetry, has to go to this orbital. Because it's asymmetrical. This electron cannot go into this orbital because it doesn't have the right symmetry. Okay? So the blue have to go to the blue, so these electrons here can go to here. This electron here, only one, can go up to here, but then it's going to come back down. This one is going to cross over and meet it here. Because remember, this is still technically in an excited state. It comes back down. And we haven't gotten into photochemistry yet. That's the T1, T2 relaxation transition. We'll talk about that in photochemistry, not here. So Zach, I forgot to bring you with us. So here's what happens in the photochemical, and I drew this without showing you. If I'm in a ring, a cyclobutene ring, thermally, I'm going to prefer to open up, okay? And I'm going to open up in a con-rotatory fashion. If I'm 4N photochemically, I'm actually going to prefer to close. But what happens with the photochemistry is I excite from side 2 to side 3. So now what happened before with my symmetry elements are flipped. Before the green worked, now the blue works. So the blue, these two electrons, symmetrical if I'm talking about disrotatory, okay? So those electrons there can go into those electrons there. This electron here, asymmetrical, can populate here. This electron here can go down here. Those will rejoin to form the product, okay? If I'm rotational, or in this case, the con-rotatory, I don't align. A goes to A, S goes to S, but notice A can't go to S. It has to go up to a higher molecular orbital, and it's forbidden. So that's how we actually derive the 4 rules. 4N thermal con, 4N plus 2 thermal dis. 4N photochemical dis, 4N plus 2 photochemical con. Okay? Now, it's your turn. Let's take the rules and see if you can predict the product. You still on? Yeah, you're still on. Okay. Let's erase our fun photochemistry. And again, you can see photochemistry is conserved. This goes dis. By the way, if you do hit this with anything under 200 nanometers, you get all kinds of, and the thought there is you're actually double exciting, and so you're getting a lot of weird rotation stuff. So this is, you can blast the molecules with way too much energy, and the rules fall apart. Okay, that is true. So it is, again, that's why I started with the 273. That's typically about the wavelength that we were irradiating these. So I want you to see if you can predict what's going to happen with this molecule. And it's a hard molecule to draw, by the way. I know. Okay, 1, 2, 3, 4. Hey, I got it. Not bad. Not bad at all. I want you to predict the product of photochemistry and thermal. Okay. So it's 10. It's 10. It should be 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. And I'll let you on a little hint. You're going to be looking. 1, 2, 3, 4, 5, 6. So you're looking at crossing right through there. Okay. And these are a lot what the homework problems are, trying to think through using the rules to predict the stereochemistry.
Hold on. I just got.
Remember, these two don't move. So when those come across, that forms your new 6-membered ring, and then these switch. So it puts them.
Oh, I was drawing my photo with my thermal. That's why I was.
Oh, were you? Were you?
Yeah, I got 'em left. Okay.
Use your pinky thumb chemistry. It's all pinky thumb. It's all pinky thumb. Okay, so let's go back. We have a 4n+2 system, so we're looking at these two, right? For 4n+2, okay, because we're 10 pi electrons. We know we're gonna form a ring across there. All right, so 4n+2 is thermal disrotatory. So if you look at these protons here, protons are my thumbs. Okay, dis is this way or down. So my thumbs on my thermal should be on the same plane, so they both protons here should be coming up. So that's my stereochemistry. Okay, where'd that come from? Came from 4n+2. I look at my rule, 4n+2 thermal disrotatory, okay? So those hydrogens are going to come up. They're out, they're in the plane of the whiteboard. They're gonna go disrotatory that way or that way, either way, it's gonna give you the same. They're either both up or both down. Okay, they're gonna go cis to one another. Now, photochemistry, the rules, pick up my feet. Photochemically, the rule says 4n+2 photo is gonna go conrotatory. So here, again, pinky thumb chemistry, con is gonna go that way, right? Or that way, con, okay? Con, with. So one's gonna be up and one's gonna be down. It's gonna give me the trans product. And it doesn't matter which one you draw. Okay, it's gonna be one or the other, okay? So the rules, can't emphasize this enough. My kids always say you got the wrong emphasis on the wrong syllable. So 4n thermal con, where the whole thing starts. Then you can just write this in, okay? This is the way you want to have this at your ready, whether it's the exam or whether it's the homework, have this ready. Because all we did here is we had to ask ourselves the question, how many electrons am I talking about? Am I 4n or 4n+2? Am I going thermal or am I going photochemical? I go back to the rule and I know 4n+2, 4n+2, photochemically, this should be a con rotation, okay? And photochemically, thermal should be a dis rotatory rotation, okay? Questions on that? Got it?
But for the other half, it's 4n, right?
Yeah, you could do, and technically you could get another product, a 4n product here. It wouldn't be very favorable because it's going to be a 1, 2, 3, 4 membered ring with a 1, 2, 3, 4, 5, 6, 7, 8 membered ring. So having an 8 and a 4, you're definitely not. I mean, and I'm not saying you wouldn't have any of that, but highly favorable to go to the 6+6. Okay. The bicyclo, 4, 4, 0 bicyclo. Cool? Okay, now to end the class today, I want to show you why this is so kind of practical and why this stuff really does matter in the real world. Leave that up here, let's take Zach over here. Okay, so if you watch, you still there, Zach? They're on the beach. Okay, so if you take this molecule here, and this is why this is really relevant even to right now in any flu season, whether it's COVID-19, COVID-20, COVID-21, we should all be taking our zinc, our vitamin D, and our vitamin C on a daily basis. Those are really important molecules for our immune system. So this molecule here, and by the way, just, I don't know if you can hear, this is vitamin D3. Actually, this is D2. D3 doesn't have saturation here. Your book is wrong. Just know that one of my pet peeves is when they mess something up. Your book has a 6-member green here on the D ring. It is a 5-member green. Okay, so just note if you do look at, if you're reading through your notes, you want to correct it, make a note. This is A, this will be B, this is C, this is D on a steroid system. When you excite this, this is why this is called, actually this is called pre-vitamin D. We're going to vitamin D, so I'm going to put pre here. Watch what happens here. Stay with me. This is why this is so incredibly cool. This is actually what my whole entire postdoc was on, so it's really personal to me because I love this stuff. I'm a 1, 2, 3, 4, 5, 6 system, right? I'm a 4M plus 2. So 4M plus 2 is photochemically, what is it? 4M plus 2 photochemically con. That tells me that if I do pinky thumb chemistry, and in this case pinky thumb, let me see if I can do that right now, okay? Pinky thumb with the methyl and the proton, watch what happens, con, right? Not dis, con. So my product that forms, and vitamin D itself, pre-vitamin D, vitamin D, all these have, notice the product that forms in this is this here. Okay, is this here, but notice my stereochemistry. Okay, again, pinky thumb chemistry, con. So this comes out, and this one goes back. And oftentimes we put it in the ring right there just to keep it out of that methyl's weight. But isn't that cool? This is exactly right now what's going on in the skin, on our skin when we need sunlight. That's the photochemistry of why we're taking a pre-vitamin D, and it's going back and forth, and it actually takes this one and then this one. If you want to really see what happens here, this does a 1,6 sigmatropic shift, which is next chapter. This is why this is so cool, because it all plays in. This proton, okay, the electrons on that proton come down here, they go down there, they kick up here, and it kicks over to grab that hydrogen. And what actually happens, and this is actually vitamin D here. So vitamin D actually looks like this. And you see how relevant this is actually, and that's coming out by the way if you want the total. Okay, vitamin D. And what actually happens is you end up with this system here. It's there. And there you go. There's vitamin D. Isn't that amazing? So you're really doing two things here. We haven't talked about sigmatropic rearrangement yet. We will. This is a sigmatropic rearrangement. What we're talking about right now is this thermal 4M plus 2 thermal con. And you can see, here's my pinky chemistry, right? Here it is, still 4M plus 2. When it goes the other way, it opens up and it puts them on the same face. This then enzymatically does the sigmatropic rearrangement. It's so cool. And you could actually even do this in the lab thermally. If you heat it up enough, it'll do that. Isn't that cool? But this is where this becomes really relevant, especially biology majors, but chemistry majors to see, you know, and Zach, you too, to see that these reactions play a huge role in our life, in chemistry, and in bigger science, not just theoretical, you know, Woodward Hoffman rules. So, okay. All right, guys, that's all I've got for you today. Zach, I'm going to put this back over in case you missed the homework problems. They're right here. Hopefully you got that. That's me. Right there. Homework problems right there. You can take a screenshot of that if you need. Okay. All right.